So there we go, we are online. And before we do that, as usual, today's Wednesday, so we are going to talk about your homework. So the homework problems that we had, that's the first one. So we have a random sample of size 4 from a distribution with density f of x equals e to negative x with x larger than 0. And the order statistic is y1, y2, y3, or y4. And the question is, find the probability that y4 is larger than 3. Because we are talking about y4 here and the sample consists of 4 observations, y4 is the maximum. And I derived the density of the maximum in the class notes, so you can use it. You don't have to take a formula to start finding out what it's equal to. So here, that's probability that y4 larger than 3 is 1 minus probability that y4 is less than 3. And this is the CDF of y4, which is f of x raised to the power 4. So it is 1 minus f of 3 raised to the power 4. And f of x for this distribution is 1 minus e to negative x. So you replace in there and you have your answer. Any question? Now the second problem was about a discrete distribution. The probability that x is equal to little x is 1/6 for all values of x 1 through 6. And this is exactly the problem that we discussed in class last time. This is cast a die, right? 6 sides, 1 through 6, probability of each of the sides 1/6. That's it right there. Show that the PMF of the smallest of the 5 observations drawn from this distribution is given by this formula. Okay, and remember that the question is about order statistics. So, you know, for every integer, the probability that x is less than y1 or equal to y1, integer y1, it's important that I choose an integer. Otherwise, I won't be able to write this formula. Because the density is this. If I want the probability that x is less than or equal to y1, it will be the sum of 1's y1 times, which is y1, divided by 6. It's a discrete distribution. You add all the observations that are less than y1, and there are y1 of them, and each of them has probability 1/6. So it is y1 over 6. And that's the CDF of the random variable x that has this distribution. Now that I have the CDF, I can find the CDF of y1, which is the smallest. The CDF of y1, that is probability that y1 is less than or equal to y1. We have also defined this in the notes. It's 1 minus probability that y1 is strictly larger than y1. Notice here, less than or equal, and here, strictly larger. And that's very important when you're dealing with discrete distributions. You can flip and still have or equal here. Because if you do so, you're including here something that is there. And the probability of getting a number for a discrete distribution is not 0. So if you put or equal here, you're wrong. Now we know that this thing is therefore 1 minus, and the probability of each of them to be larger than y1 is 1 minus the CDF of x at y1 raised to the power 5, because we have 5 observations. And the CDF is what we got here, y1 over 6. So that is 1 minus y1 over 6. And this is technically 1 minus 6 minus y1 over 6. Now, after writing this formula, I can now find the value of capital F of Fy1 of y1 minus 1, the previous number before y1. That gives me 1 minus, I replace y1 by y1 minus 1. So that's the formula. Now, how do I find the value of the PMF at y1? Your class notes from the first 2 lectures say, for a discrete distribution, the value of the PMF at a point is equal to the difference between f at that point and at the previous point. So f of y1 minus capital F of y1 minus 1 is going to give you the little j1 of y1, which is the value of the PMF at y1. And you put that down, that's exactly what they ask you to prove. And the question was, why is it that the formulas that you have in the lectures don't work in this problem? First, those formulas were derived for continuous distributions where you can take derivatives to find the density. You can't take derivatives to find the density of a discrete distribution because you have a PMF. Rather, this is what we do for a discrete distribution. We subtract the value of the CDF and at the point and the value at the previous point. That's one of the reasons. And secondly, when you have discrete random variables and you take a sample and you want to do the order statistics thing, the probability of having the smallest equal to the second smallest is not 0. The probability of y1 equal capital Y2 is not 0 for discrete distributions. But for continuous distributions, it is 0. Okay? That's the reason why those formulas that you have there cannot work in this case. Any questions on this? When you're using those formulas, always remember that they have to do only with continuous distributions. Any questions on this problem? Any need of explanations? All right. If not, we move on. Now, the third problem is about order statistics of 5 random numbers, a random sample of size 5 from a distribution f of x equal e to negative x, x larger than 0, the same distribution we had in the previous problem. And the question is, show that z1 equal y1 and z2 equal y4 minus y2 are independent for this distribution. It doesn't mean always. That's one of the properties of this distribution. And so how do you do that? The hint is given in the problem. Find first the joint distribution of y2 and y4. That's where you use the formula as given in the notes. The joint distribution of y2, y4 is equal to that. That's just applying the formula, in which capital F of x is 1 minus e to negative x, and little f of x is what is given right here, e to negative x. Therefore, we replace those two things into this formula and compute. This is what we get. So what I further did here, knowing what the question is about, is from this line to this line, I remove e to negative y2 from this formula. So which means I multiply this by e to negative e to y2. Therefore, it becomes e to negative y4 plus y2, which is keeping the minus out. That will be y4 minus y2. And the minus and the e to the y2 that I multiply by, I put it outside. That's why it comes to this one. And now you have minus 2 times y4 plus y2. So that's the sum of all these 1, 2, 3, and the fourth coming from here. So when I do this algebra, the reason why I do that is that I know where I'm going. I know that I want a function of y4 minus y2 and y2 itself, because that's how you get that the density, the two random variables could be independent if the joint density can be written as a product of the two densities, which means product of two functions, one of y1 minus y2 minus y4, and one of y2. So after doing that, now I go by the formula. This formula here, this work here is one of the homework problems that we had. And this is the reason why we were doing that problem. When you have to find the distribution of y, I asked you to find the distribution of x minus y and y. Do you remember a problem like that? So that's exactly the same work that I did then that I repeated here by replacing those variables that were there by z1 and z2. If you're smart enough to be using transformations, you use them, but I don't. I repeat the same work I gave you then to find out that the joint distribution of z1, z2 is nothing but the joint distribution of y2, y4 applied to the point z1 and z2 plus y1. You can check the steps. It's the same steps that we had back then. Therefore, if this is true, then f z1, z2 of little z1, little z2 equals, and I replace, therefore, in the formula that we got here, z1 stands for the first component inside that. So z1 is going to go in for y2, and z2 plus z1 is going to go in for y4. So into this formula, I will replace y2 plus y4. Sorry, I will replace y4 by z2 plus z1, y2 by z1. When I do so, this is what happens. So you have 120, 1 minus e to the z1, that is replacing y2. Then 1 minus, here is replacing the other guy. Why is it z2? Because that's y4 minus y2, right? So y4 is this, minus y2 this, z1 plus z2 minus z1 is z2. Then I go to this one, and I have y4 plus y2, so this plus this times 2. That will give me 2z1 plus z2 times 2. That gives me 4z1 plus 2z2, and the minus sign that's out. That's why we get this. Now you can look at this formula. You can see that I can regroup the terms that have z1 and regroup the terms that have Z2. When I do that, the terms that have Z1 go together, and the term that has Z2 go together. And this is a function of Z1 times a function of Z2. Therefore, the two random variables are independent. That's how you show that two random variables are independent. Questions on this? In this proof, at the end here, you don't need to prove that this is exactly a distribution and that is exactly a distribution. All you need is to show that it's a function of Z1 times a function of Z2. The constant of integration that makes it 1 doesn't matter in the proof because it doesn't contain Z1 or Z2. Any questions? So everybody will be able to do this if I ask you that on the test, right? Silence means everything is okay. Now the next problem is about a random sample of size 2 from the normal distribution. So you have a random sample of size 2 from the normal distribution, and you want to show that the expected value of the minimum is equal to negative sigma over square root of pi. All right. So how do we do? Again, anytime you want to find the expected value of a random variable, the first thing that comes to mind is get the distribution of that random variable. What's the distribution of y1, y2? The distribution of y1, y2, by definition, it is factorial 2 because we have two random variables times the product of the distributions at the points y1 and y2 with the condition that y1 is less than y2. That's the definition, right? That's what we have. Therefore, to take the expected value of y1, we need to integrate over this range with y1 less than y2, y1 times the density that you have. The hint in the exercise says integrate first with respect to y1, then with respect to y2. That's for a reason. Because when you do integrate first with respect to y1, what you get is a simple integral that you can compute the substitution. So I set up my integral. Y1 has to be less than y2. That's why I will integrate first with respect to y1 from negative infinity to y2. And therefore, afterwards, integrate with respect to y2 from negative infinity to infinity. How do I compute this integral? Notice that this is an exponential, and the other part, y2 squared over 2 sigma squared, has nothing to do with y1, so it can stay out of the integral. So I can just compute the integral with the first one, which is this thing that I wrote here to compute. Integral from negative infinity to y2 of y1 e to negative y1 squared over 2 sigma squared dy1. Like I said, this is a simple u substitution thing. This thing that stands here is a derivative of what is up there up to negative sigma squared that is missing. So you do u substitution, you integrate, you get this. So that integral equals this. From negative infinity to y2. When you plug in y2, that's what you get. When you plug in negative infinity, you get 0. So this is what the integral is equal to. the integral that is inside. Now you take that integral that is inside, which you got here, and you plug in here. And don't forget when you're plugging it in, that was just half of what was inside. You still have inside e to the negative y2 squared over 2 sigma squared. So that's it. And the other one is the one we just got here is right here. And when you add the two things, you see they are equal. So when you're adding, that just erases the 1/2. So the whole thing equals this. Now, when you get this integral and you start thinking, you need to remember that it is statistics. Nobody wants you to be doing crazy things. If that thing showed up in front of you, it is probably a distribution. And you need to just figure out what distribution it is to make sure you state that the integral will be equal to 1, and then you move on. And when you look carefully at this thing here, you can see that this is an incomplete distribution of the standard normal, where the variance equal to 2 sigma squared. I'm sorry, sigma squared over 2, with the variance equals sigma squared over 2. Because you know that for a normal distribution, inside here should be y squared over 2 sigma squared. If you don't have 2, that means the variance is sigma squared over 2. And because the variance is sigma squared over 2, you think of the density of the normal distribution with mean 0 because there is nothing apart from the square, and variance sigma squared over 2, and you need to complete that distribution. What is missing for this to be the distribution? What is missing is square root of 2 pi times the variance. And the variance is sigma squared over 2. The 2 pi times sigma squared over 2 is 2 pi. It is pi sigma squared. So you put that here, and you make sure you complete it to have exactly what was there. And that is completed by having sigma over square root of pi. So if you multiply all this, you will get negative 1 over pi. If I multiply this thing here and that gives me the negative 1 over pi that is there. But now the good news is this here is exactly the density of the normal distribution with mean 0 and variance sigma squared over 2. Ta-da! The integral is 1. I don't need to compute. So that integral is 1 because it's the density. Therefore, 1 times this, we get that the mean of the minimum is negative sigma over square root of pi, which is what the problem was asking you to show. Now, the second part of the question is actually the easiest of them, but if you don't use the properties, it will be the most difficult. How do I use the properties to answer this question without solving? Look at this simple but very important fact. If I have two observations, x1 and x2, I add the minimum of the two and the maximum of the two. Is it different from x1 plus x2? I take two numbers. I take the maximum of the two numbers and the minimum of the two numbers, and I add them. If I take those numbers and I don't think of looking for minimum or maximum and I add the two, is there a difference between the two things? No. So the minimum plus the maximum, it's x1 plus x2 anyways. Therefore, the expected value is equal also. So the expected value of y1 plus expected value of y2 is actually expected value of x1 plus expected value of x2. And they all come from normal distribution would mean 0, so this is 0. And therefore, the expected value of y2 is the opposite of the expected value of y1, which is sigma over root pi. No computations. Now the second part is also as easy. You just don't even need to compute the integral. You write these two things. It's the same density that we had up there. So you just copy that same integral and then you add y2, right? Now you have y1 and y2 in there. And you write in the same order. The same first integral that we already computed. We just take it and put inside. We already computed that integral. So we don't need to do that job again. We had it, that's it. And we multiply that by y2. And guess what? I don't even need to compute this integral the way I did. I look at this and I say, this is a symmetric function. This is an odd function. The integral of an odd function over a symmetric region, calc 4 equals 0. You don't even need to compute it, right? You have an odd function that you're integrating over a symmetric region. The answer is 0, no matter how crazy the function that is inside is. As long as it is odd, the integral is going to be 0. So you don't even need to compute this. And because the expected value of y1, y2 is 0, therefore the covariance is 0 minus expected value of y1 times expected value of y2, which is sigma squared over pi. Questions? Now, if you don't take this path and you try something else, you will end up with a lot more work and maybe the same final answer. Maybe you would not have enough strength to go to the end. All right. Question. Baselines here. Now the next problem is where I
expected value of y2 would be the same as the.
What?
I thought the expected value of y2 would be the same as the expected value of y1.
Why would that be the case if y2 is the maximum and y1 is the minimum? Right? So intuitively, that wouldn't be the case, right? If they are equal, that means the two random variables are just the same. They should not be equal under any circumstances. And the up and in the proof here shows you that they actually have to be opposite to each other always when you have only two observations, because the proof that I gave there had nothing to do with the distribution. It's just after the answer that I use the computations to get the answer. They are always opposite to each other when you just have what I see. So the point being, you shouldn't expect that the expected value of y1 is equal to the expected value of y2, because y1 is always the minimum and y2 is always the maximum. Now, the good thing about this other problem and the thing that I was saying that always equal to the opposite, it's not true. Okay, it's not always equal to the opposite. That is, it's equal to the opposite if the expected value of the underlying distribution is 0, right? Because we did use that fact. We did use the fact that expected value of x1 is 0, expected value of x2 is 0, to get that it's the opposite. All right, so this problem has a lot of thinking involved. All right. And I saw some people writing an answer with just AI equals and giving a formula. I don't know where that formula comes from. If you don't have a work that shows the formula, it's better don't use it. Because the exercise consists actually of deriving that formula that you're using. So here, how do we do? Look, we look at this problem. It says we have a random sample, x1 up to xn, from a distribution of any type. And we define G equal sum, j from 2 to n, of sum I from 1 through j minus 1 of absolute value of xi minus xj divided by choose 2 out of n. And I just, because the question is in the section of order statistics, you should understand that you can use the properties of order statistics to answer the question. Okay? So here we call y1 through yn the order statistics from x1 to xn. And the question says, if n equals 10, find a1, a2 up to a2, a10 such that j equals sum I from 1 through 10, ai, yi. Why is this possible? Because the xi's are actually those yi's. It's all those same yi's given in a certain order, in ascending order, y1 less than y2 less than y3 less than and so on. So when we are adding all these things, it makes sense to think that in the end, it might be a linear function of the order statistics. And the question is, first of all, you need to prove that this is possible, and in proving it, find out what are the AIs. So what I do is I prove all this in general. I answer the question in general. Then at the end, you can put it n equal 10 and find what you find. But I answer the question for any n. Before doing that, I want to draw a table to explain to you why the formulas that I'm using here work. Okay? So when you're having a double summation, when we're having a double summation, we need to understand by a table what the double summation is about. So we said sum j from 2 through n of sum I from 1 through j minus 1. So once you fix j, I never goes up to j. I stops at j minus 1. And then inside, you have absolute value of xi minus xj. I don't care about the other coefficient that we have there. I could just pull it outside here. Now, I want to show you graphically what this actually means. So assume that this is a table in which I have, let's say along this axis, I have I, and along this axis, I have j. And I want to show you what this sum is going to go. So it goes all the way up to n for each of them. And let's say we have these lines that are telling us where the things are. And so on, all the way down to the last one that will have n. And then you have the same thing here. 1, got 2, got 3, and then all the way down to the last one that contains the nth norm. So you are going 1, 2, 3, 4 down to n. You're going 1, 2, 3 down to n. Because I never goes up to j, that means that the diagonal is not accounted for. Because diagonal is I equals j. That's what it means. The diagonal doesn't exist. And all the way down to this last diagonal element, that is not there. All that diagonal. How many elements are on that diagonal? Huh? N. So we have n diagonal elements. So it's important. And we say once we fix j, I goes from what? 1 through j minus 1. And we fix j starting from 2, right? So that's it. We fix j starting from 2. So we fix j starting from here. And I goes from 1 to j minus 1, which is here. If I fix j equals 3, I goes from 1 through 2, right? Do we agree? If I fix j equals 4, I goes up to 3. So what we are doing is adding the numbers that are on the upper diagonal here, right? Technically, what that means is we are adding the upper diagonal elements. Let me better to fit what I'm trying to do. It's better to have my I here and the j there. Okay, j here and I here. So I fix my j starting from 2, and I goes from 1 through 1 less than 2. So it's this. When I take j equal 3, I goes from 1 through 2, right? So that is 1, 2. When I take j equal 4, I is 1, 2, 3, 1, 2, 3. So it's the upper diagonal things that you're adding. Does that make sense now? So we are adding these things 1, 2, 3, 4, 5, 6, all the way down to here, all these. So we are adding all the upper diagonal elements. How many elements are there? That's n times n minus 1. So these are this is the number of elements that we are adding. Now, when you look at this formula, what happens when actually I equals j? What's this? It's 0. So it actually doesn't matter if I continue this thing all the way up to j. Because anyways, I will be adding zeros at that position. Which means it doesn't bother me that this thing is not here. On the other side, all the numbers that are up there that you're adding are the same numbers that are down here. Do you agree with that? So the sum that we have here is nothing but half of the sum of everything that is in this. Do you agree? That's the proof. That's the reason why I was drawing this for you to see. So the sum that we have in this formula is nothing but half of the sum of the whole thing, because what is up there is the same thing that is down here. Do you agree? Because we have absolute value. One of them is xi minus xj, the other one is xj minus xi. But the absolute value is the same. Therefore, that's the reason why I say that my sum is equal to 1/2. The difference between that formula and this is that now here I have 1/2. And I add everything that is inside. I add everything that is inside the triangle, inside the square. Why now having the order statistics? Because when I'm adding everything with the absolute value, it is the same thing as adding the order statistics, because this is just a different arrangement of those order statistics. Same as for when you have the previous problem I said, when you have x1 and x2, you find the minimum and the maximum, you add them. It is the same thing as adding the original variables. This is the same argument here. And that's the reason why I included everything. When I include everything and I'm adding everything inside that square, it is same as if I was adding the order statistics. Does that make sense? So because I'm adding everything, this sum therefore is equal to that, having in place of the xi's the order statistics. Why the transition to order statistics? Because now that I have the order statistics, I know that when I is larger than j, xi is larger than xj, and I can remove the absolute values easily from the order statistics. Does that make sense? That's the reason why. So I did this to be able to use the properties of the order statistics. And the explanation I'm giving here is that it's the sum of all differences of variables selected 2 by 2 from x1 all the way up to xn, and yn to y1 through yn is just an ordering of these variables. So it's the same thing that you're adding, the same differences that you're adding. No matter in what order you put the numbers, you select them 2 by 2, get the differences, take absolute value, it's the same thing, right? So, and the two, that's the reason of the two I explained on the box there. Now, because the diagonal element is 0, because the diagonal elements are 0, this now is just, see the game I play here? Because the absolute value of xi minus xj, sorry, the absolute value of yi minus yj, when I'm taking it, is the opposite of yj minus yi. If I was writing them on the other side, I just decide now to add only one side. I decide to add only one side of the rectangle and multiply by 2, because I know the other half is also equal. The same argument that we started with. So we went from half to full to use order statistics and went back to half with the order statistics already. But this time, we don't have absolute values anymore, because we are taking the sum in such a way that yj is always larger than yi. Is this making any sense? No, because this is true, we don't have absolute values anymore. We have the 2, and that 2 will cancel the other one. Now the difference between this formula and the original is now you don't have absolute values anymore, but you have the yi's and yj's in there. And all you have to do now, that's where, see the reason I wrote here? All you have to do now is open the parentheses now and compute the sums. When you do so, the first, when you are adding with respect to I, j is a constant. You're adding j minus 1 thing, so it gives you j minus 1 times yj. And then the second part remains sum of yi's, I from 1 through j minus 1. So we got that. And now I split the two things. I take this separately and the other one separately. Now I have sum j from 2 through n of what I had minus this sum goes inside j from 2 through n and I from 1 through j minus 1 of yi. Okay. This first guy stays. Now I want to modify this one. Using the same idea that I used in the other one. This sum, if you look carefully, you see that this is the same kind of sum. It is the same kind of sum that we had in the other case. Now we want to flip it and add. It's what you call an integration. It's called changing the order of integration, right? When you have an integral with two variables, you change the order of integration. When you have double sum, you can change the order of the sum. But when you're changing the order of the sum, you need to make sure you remember what the boundary of the summation is. So here I will change the order of summation from I first, then j to j first, then I. When I do that, using the same table that I have here, and let me explain that to you. So here, if we said here that when we take j, we go with I from 1 through j minus 1. Let's say I flip now, I want to start adding from I fix I. Whenever I fix I, what am I adding? When I fix I, I'm adding things starting from here, right? And the number right here, what is it? Right on the diagonal, what's the number? If I have I here. What's the diagonal in a square? I. If I have I here, right here I have I, and what am I using? This here, which is I plus 1. So I will have to add from I plus 1 through n. That's why it turns here into sum j from I plus 1 through n. And then now after doing that, add with respect to I from 1 through, look at that same table. I will go from 1 all the way to n minus 1, because if you take n, there is nothing to add for n. You see that? For n, you should be adding things here. There is nothing there. So I goes from 1 through n minus 1. That's why in here, that sum turned into this. Okay. Now we can add the things that are inside because yi has nothing to do with j. It's a constant. So this constant comes out, and the sum of ones, how many ones are from I plus 1 through n? It's n minus I. So that sum inside is n minus I times yi, and you remain with sum I from 1 through n minus 1. So this is simple all the way down to this. And now you need to understand why you have j2 here through n, and I is 1 through n minus 1. Now the answer is simple for j equal 2 because you have j minus 1 here. So if j is 1, this is 0. So I can include 1 here without problem. That's why I included 1. The difference from here to here, I included 1 here, knowing I'm not changing anything because 1 minus 1 is 0. And in the second one, I included n, knowing that n minus n is 0. So this also goes up to n. And now I have a sum j from 1 through n, j from 1 through n. So I just need to subtract the two things that are there. And that gives me 2j minus 1 minus n. And therefore, you get aj equals 2j minus 1 minus n over. Choose 2 out of n, which is 2j minus 11 over choose 2 out of n. And if you want to plug in n equal 10, you will see what the aj's are equal to. Questions? Any questions? I use n equal 10 here. The bottom should be 10 as well. Which is factorial 10 over factorial 8 times factorial 2, which is 10 times 9 over 2, that's 45. So this is 2j minus 11 over 45.
Dr. Longlaw,
Yes?
so when you had 1 over 2 times n choose 2, and then you had the 2 in the parentheses earlier, and you dropped the absolute value, you put the 2, you multiplied the 2 times those two sums because you dropped the absolute value?
No, while doing that, I said that I'm adding half
Uh-huh.
all the way up to j minus 1. So I'm adding half of the rectangle, and the other half is the 2 you have, because the two halves are equal. You're adding things inside this rectangle. The things that are here are the same things that are here. The opposite, what is here is the opposite of what is here. The absolute values are same. So if I'm adding only these, I multiply it by 2, then I'm adding everything in absolute value. That's why you have the 2. Does that make sense?
I thought that second half of the table you showed didn't exist, because I can only go up to,
Why wouldn't it exist if that's the reason why I got the sum up to n and up to n everywhere? That's what I explained. I created that table for you to have a sum over the square. This sum is over the square. And now from that square, I'm getting down to half of the square. In the next part, they ask you, when the xi's are IID from the normal distribution with mean mu and variance sigma squared, show that the expected value of j is equal to 2 sigma over square root of pi. And then I wrote something here, and then I wrote an alternative. If you don't have the ideas that I used to give this answer, you can use this as an alternative way of answering the question. Just redefine Ci as xi minus mu over sigma and work with the sample from the normal 0, 1 because Ci will be standard normal. And then you do the calculations. Now, and that will be true because you're dealing with xi minus xj. And if you do this transformation, the expected value of this random variable will be 0. So anyway, if you don't do that, you just start computing and you say the expected value of j is equal to 1 over 2 and choose 2 out of n, then you compute the expected values that are here. And then these expected values are all equal because it's IID. So expected value of xi minus xj are all equal, no matter what is I and j, and I is not equal to j. So they are all equal. Each of these things is equal to the expected value of x1 minus x2. And to make my life easier, I just completed the whole thing to have the full square again, but I didn't have to do that. If I know that here I have exactly n squared minus n over n things that I'm adding, which is what I proved here. It's n squared minus n over 2 terms that I'm adding, right? So if I don't want to complete this thing here, I can just use that fact that I already proved here, that I'm adding n times n minus 1 over 2, which is n squared minus n over 2 things. That's why I have n squared minus 2 over 2. And then this number that was out, an expected value of absolute value of x1 minus x2. And choose 2 out of n is exactly n squared minus n over 2. So this ratio is 1. Therefore, the expected value of g is equal to the expected value of absolute value of x1 minus x2. But if you remember the previous problem we just answered, it's exactly that. Find the expected value of absolute value of x1 minus x2, which is the same. And so here, expected value of absolute value of x1 minus x2, what is it? The absolute value of x1 minus x2, I say, is always y2 minus y1. Do you agree with that? This is a shortcut to answer the question. Do you agree that the expected value, that the absolute value of the difference of two numbers is equal to the largest minus the smallest? Right? That's without probability theory. So the absolute value of x2 minus x1 equals y2 minus y1 because y2 is the largest of the two and y1 is the smallest of the two. Now I put a expected value around it. Now using the properties of these, I get that this is expected value of y2 minus expected value of y1. But when the mean is 0, as we assume, the previous problem stated that the expected value of y2 is equal to the opposite of the expected value of y1. That's what we did in the previous problem. So this thing is twice the expected value of y2. But in that previous exercise, we got the expected value of y2 equals sigma over root pi. So the answer is 2 sigma over root pi. I don't need to compute any integrals. So this is the issue that we have with these things, that questions that you're answering tend to be linked to each other in certain ways. That if you see, it will make your work easier. Okay. But if you don't see that, then you will do a lot of work before finding the answer. Because if here I don't remember that previous problem. I'm going to compute those integrals here again, right? To figure out, find the joint distribution of y1, y2, and use it to find the expected values, right? You know how many pages I will have more. So, all right. Any questions on this one, on that second part? We don't have a question. I think the next problem was probably the easiest problem of this homework. You have an order statistics y1 through yn of a random sample from x distribution 3x squared over theta cubed. And then you need to show that the probability that c is less than yn over theta less than 1 equals 1 minus c to the power 3n. How's that? Well, first of all, we find the CDF of x. That CDF is the integral, it's x cubed over theta cubed when x is between 0 and 1. Then the CDF of yn, which is the largest of the observations, in your class notes you have that formula. The CDF of yn is the CDF of the original variable raised to the power n. So that is x cubed over theta cubed raised to the power n. So x to the power 3n over theta to the 3n. Now, this probability is equal to the probability that c theta less than yn less than theta. So that is Fyn of theta minus Fyn of c theta, which is obtained by plugging into the formula of Fyn theta, then c theta. And then when you plug that in, they cancel, you get this answer, 1 minus c to the power 3. And the second part of the question says, take n equals 4, y4 equals 2.3, and find a 95% confidence interval. What that question means is just construct the confidence interval for theta based on the formula that you have here. So you solve for theta, and you find that theta is between yn and yn over c. So this is the interval that you can build. And all you need to do is find the value of c for the probability of this event to be 0.95. That's it. And that probability of that event is 1 minus c to the 3n, which is part A. So you're solving 1 minus c to the 3n equal 0.95. So you get the value of c, and you put that here, and you have your confidence interval, where yn is the 2.3 you have here. Yn is 2.3, and c is what you just got here. Questions for this problem? It. Now the next problem is now 4.5.3 testing. So you have a random variable from PDF f of x equal theta times x to the theta minus 1 with x between 0 and 1, and theta is in the set 1, 2. And you want to test h0 theta equal 1 versus h1 theta equals 2 using a random sample of size 2 x1 x2. The critical region is given by c equal to the set of all x1 x2 such that 3 over 4 is less than or equal to x1 x2. Find the power function. So the power function, it has to be defined in the book for values of theta that are in the alternative, right? So that's why I started right away, I put 2 there. Because you are defining under the alternative the probability of C. And that is probability that 3/4 less than x1 times x2. And you want to solve this thing. It's probability that 3/4x2 is less than x1 less than 1. And remember that this thing I'm solving here is with x1 and x2 between 0 and 1. So I have the right to divide by x2. x2 is positive. That's why. Otherwise, I wouldn't be able to do that. But after dividing, you will still have to explain to me how you get this boundary that we are integrating from 3/4 to 1. From 3/4x2 to 1, I understand from this. But where is this one coming from? And you've got to know that if it's written like this, then 3/4x2 is less than 1. Therefore, x2 is larger than 3/4. That's why. It's not just a claim, it's from the formula that is written here. So your integral is going to be over these values of x1 under the condition that x2 is larger than 3/4, and therefore between 3/4 and 1, because x2 is less than 1. So integral 3/4 to 1, and the rest is easy, just product of distributions, integrate, plug them in, and then you get that. Then you plug in theta equals 2, and then you get this. That's it. The only difficult thing in that problem was to figure out the boundary that you need to use here. Question? Now the other problem of the same kind, now a binomial NP, and P is possible to be 1/2 of 4. So that's the set capital omega. And the null hypothesis is to test P equal 1/2 versus H1 P equals 1/4. So the alternative has only one value of theta, 1/4. And you use a random sample of size 1, x1. And it says the rejection rule is reject H0 if x1 is less than 3. That's the rule. Question, find alpha and gamma. What is alpha? Alpha is the probability to under H0 of the critical region that is given. And H0 is P equal 1/2. So that's probability under theta equal 1/2 of the critical region, x1 less than 3. x1 less than or equal to 3 means x1 equals 0, 1, 2, 3. Under theta equal 1/2. And that's how you would compute the probability. It's a binomial sum of the probabilities. Then, second part, the power gamma. It's under the alternative then. Probability under theta equal 1/4 of that same critical region, x1 less than or equal to 3. It's the same formula, just that now P is different. P is 1/4. So it's 1/4 and 3/4 that you're using there. Questions? The last problem is with the normal distribution, our old friend, the normal distribution. So we have x that follows the normal with mean theta and variance 5,000 squared. Huge. A random sample of size n, x1 through xn is selected. And the critical region, same as in the other problem, is defined as X bar larger than or equal to C. H naught is theta equals 30,000 versus H1 theta larger than 30,000. Determine N and C for which gamma, which is the power function of 30,000 is 0.01, gamma of 35,000 is 0.98. What's the definition of gamma? It's the probability of the critical region under H1. So it's the probability under theta that X bar is larger than C. That's the critical region, X bar larger than C. So X bar larger than C, and you have a standard, you have a normal distribution, then X bar also follows the normal distribution with variance sigma squared over n. And you standardize knowing that the mean is theta. So that will be square root of n times X bar minus theta over mu. That's a z-score larger than or equal to that. So you get probability of z larger than root n, c minus theta over sigma. That's the function gamma of c. And you want gamma of 30,000 to be 0.01, which will mean go to the z table and look for the number that gives you the probability 0.01. That's 2.325, whatever you can have could be close to that. Gamma of 35,000, you want it to be 0.98. You go to your z table and you find that number. It's negative because this is too large. And you want the probability to be larger than something to be 0.98. The number you're looking for better be negative. So that's negative 2.055. And now you want to solve this system of two equations to find n and c. The easiest way to do that, when I look at this, I see the answer. How? Just subtract the two things. I take this minus that, the c's cancel, 30 minus 30,000 minus 35,000, it's 5,000. So that's square root of n times 5,000 over 5,000 equals 4.3. So the answer is square root of n equals 4.38. So n is the square of that, which is approximately 20. After getting that, you solve for c. Taking any of the two and solve for c, you get that c is 32,654 point something. And you say the end. Any questions on this one? Any questions? No. All right. Fortunately, or maybe fortunately, we had to spend the whole time on those problems, and therefore, next time we will be talking about convergence in probability and consistency, which I defined today, perhaps. That's the definition of convergence and probability. If we have a random variable xn, a sequence of random variables xn, and a random variable x that are defined on the same sample space as xn, we say that xn converges in probability to x if for all epsilon positive, the probability that absolute value of xn minus x is larger than or equal to epsilon is equal to 0 in the limit as n goes to infinity. And that is equivalent to requiring that the probability that absolute value of xn minus x strictly less than epsilon is equal to 1 when n goes to infinity. The notation for that is xn converges in probability to x. From that, you have one of the theorems that you need to remember from this course, which is called the weak law of large numbers. Let xn be a sequence of IID random variables with mean mu and variance sigma squared, which means if I have a random sample from any distribution that has mean mu and variance sigma squared, then the sample mean converges in distribution to the true mean. Wow. That's the reason why we do statistics, right? Because this is telling you that when you take enough information from a population, the average of the things that you're taking is going to tell you exactly what that population is about, which is mu. Which means what? That the probability that x bar is away from mu as n goes to infinity, that probability is 0. The probability that x bar be far from mu is 0 when n goes to infinity. So your mean is really, your sample mean is really a good estimator of the population mean. And the proof of it is simple. I provide here a proof that is a little different from the one that you see in the book. I take every epsilon, put this one. Because I have absolute value, I can square these. When I square it, I get this. From this square, I can apply the Markov inequality, which states that this probability is less than the expected value of what I have here divided by the number that is here. And this expected value is nothing but sigma squared over n, because that's the variance of x bar. The variance of x bar is sigma squared over n divided by sigma squared. And then you take the limit when n goes to infinity. You have that 0 is less than or equal to that limit, but the limit is less than the limit of sigma squared over n epsilon squared. Sigma squared is a constant, epsilon squared is a constant. This limit is 0. By the squeeze theorem, you have 0 on the left, 0 on the right. The limit that is in between is also 0. That's why it is true, sample mean converges in probability to the population mean, which also means in other terms that the sample mean is a consistent estimator of mean. See you next time.